Now the next is general solution of Bessel's equation. General solution means we know that the Bessel's equation is of the form x square y double dash plus x y dash plus x square minus p square y equal to 0, where p is greater than or equal to 0. General solution means it is of the form c1 y1x plus c2 y2x. So we have already calculated what is y1 in the previous one of the lecture. We have discussed that one of the solution is in the type of Bessel's function. Now the question is to calculate the another solution, that is y2. So we'll write this as a theorem. Is prove that the general solution of Bessel's equation, that is this, is given by first one, if p is not integer, this p is not an integer, then it is y equal to c1 jp plus c2 j minus p x. If it is not integer, then it is there. And also in the previous lecture, we have proved that this jp and jp minus j minus p are linearly dependent if p is an integer. If p is an integer or non-negative integer, we have proved that. So in that case, we cannot write this as a general solution. So if p equal to m is an integer, then it will be y equal to c1 jm of x plus c2 y m of x, where what is this y m of x, where this y m of x will be limit of p tends to m yp of x, and where this yp of x is cos p into pi jp of x minus j minus p of x upon sine p pi. So this is the expression for which we have, it is a general solution for this one. So here we will see that, or we have already done that the general one of the solution of this Bessel's equation is of the form Jp of x, that we already proved in one of the lecture. So let us write that is here. So let's say proof of this. Consider the Bessel's equation of order p as x square y double dash plus x y dash plus x square minus p square y equal to 0, and p is greater than or equal to 0, we'll call it this is 1. We know that, or we, by previous one of the lecture, we have discussed that the Frobenius solution for m1 equal to p is the Bessel's function of the first kind is Jp of x is equal to summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus p factorial into x by 2 power 2n plus p. We call it this is 2. And also we have calculated what are the roots of the identical equation. The roots of identical equation are m1 equal to p and m2 equal to minus p. Now there will be cases, two cases. If m1 minus m2, then you know that the Fubini's method, if it is non-zero or not a positive integer, then second solution is just by replacing this as m by minus m. That is your second solution, or and which is the linear independent with the second one. So that is by Fubini's method we call. So let us write that if m1 minus m2 will be p minus of minus p, which is 2p, is non-zero and non-positive integer. This is very important thing. If it is not zero and not positive integer, then it has second Fubini's solution, which will be independent of the first solution, which will be independent from the first solution. First solution we already have y1 is equal to jp of x, which we already discussed. Now the corresponding to m2, which is minus p, we obtain the Fubini's solution from whatever the things we got from here, from or by replacing p by minus p into that. So the second solution is jp minus m of x, which is summation n running from 0 to infinity minus 1 raised to n upon n factorial into minus p plus n factorial x by 2 power 2n plus p. This is the second solution we get. This is called the second Bessel's function. This is called the Bessel's function for second kind. This is called Bessel's function of second kind. Okay, so this is the solution, that is the proof of, or I can say, which can be solved here. If it is not a positive or it is not an integer or zero, then we have this is the solution. Then the general solution is there. Now, if this p or I can say this m1 minus m2, which we have here, it is an integer. Again, here it is positive, so in general it is has to be integer. Then this p is replaced by minus p and minus p is replaced by p. So that is, note that 2p is not an integer if p is not integer, and all not half of an odd integer. So half of that, that is, if this is not integer, p is not integer. So if p is not an integer and not an odd integer, then the general solution can be written as y equal to c1 y1 plus c2 y2, which is c1 jp of x plus c2 j minus p of x is the general solution of Bessel's equation. Okay, so that we have did here. Now case number 1, that is, let p be a half of an odd integer. See, why we have taken this is p is not an integer and not a half of a positive integer, because it is a 2p. m1 minus m2 is 2p. So if p is not integer, it may possible that it is at half of that value. That means p, the half of that this value will be integer. So that's why if p is a half of the odd integer, then in the recurrence relation, let us recall what is the recurrence relation we have into the Bessel's function. Let us recall that. The recurrence relation we got for the Bessel's function, let me write that, is this 2p plus 1 a1 equal to 0 and an will be minus an minus 2 upon n into 2p plus n. And from this we say that this p is positive, so that's why this will never be 0. So now it is 2p plus 1 is there. So this p we have taken is a half of odd integer. So due to that, we can say that due to this one, we can say that this minus of 2p plus 1, a1 equal to 0. and that is the another quantity is there, that is n into minus 2t plus n an plus an minus 2 is 0, and this is 2 for n is running from 3 to 4 up to so on. If p is equal to 1 by 2 and n is 1, if p is 1 by 2, then we know that this is 0. So in that case, you will have 0 into a1. Then we will have minus 2 into 1 by 2 plus 1 into a1 equal to 0. This will implies 0 into a1 is 0. So in that case, you cannot able to find out what is the value of a1. May or may not be 0. So in this case, a1 need not be 0. You cannot say it will be 0. As we have discussed into the finding the Bessel function, we say that this 2p plus 1 is never be 0, so that's why a1 is 0, and then we conclude about this to write down this in the form of a jp. But here that is not the case. So but since we required a particular solution, we choose a particular value, that is a1 equal to 0. So we'll require the particular solution. So in the particularly we can choose this a1 is 0. So we'll have no problem with this jp. We can achieve as we have discussed earlier. Now if the second thing, if p is 1 by 3 by 2 and n equal to 3, then as per this second equation, that is n into minus 2p plus n. So n is 3, we have written 3, minus 2p into, that is minus 2 into plus 3 plus 3a3 plus a1 equal to 0, that is n equal to 3 we are substituting here. But this will implies this quantity will be 0. So 0 into a3, a1 is already in particularly we have taken it as 0. So 0 into a3 is 0. So that means here also we can say that hence there is no need to take a3 equal to 0, but to get a required particular solution, we choose this a3 is 0. So here is also we choose this a3 is 0. And similarly for next one is 5 by 2 and n equal to 5. The same situation will occur. So we can similarly say that solve this problem, we choose. So every time we have occurring the same situation, we'll choose that a1 is 0, a3 is 0, a5 is 0, and so on. Then we get the required particular solution will be y2 is j of minus p, which is equal to summation n running from 0 to infinity minus 1 raised to n upon n factorial into n plus p factorial x by 2 power 2n plus p. This is the situation we got. So the first term of y2, that is, what is the first term when n equal to 0? So we note that the first term of y2 is j minus p of x is n equal to 0. If I substitute, that is minus 1 raised to 0 upon 0 factorial 0 plus p factorial into x by 2 power 2n plus, sorry, n, that is 0 plus p. So that will gives you 1 upon, but the value of p is minus, so this is minus p. Here is also minus, this is minus p is there, so this will be minus p. Here you will have minus p. Yeah, so this is n minus p and this is minus p here, so that's why it is minus p minus p. So this is minus p factorial. This is x by 2 power minus p, so I can write down this is 1 upon minus p factorial 2 by p, 2 by x raised to p. It is unbounded because this is the things we have, so it is unbounded for x is equal to 0. If x is 0, then it is unbounded. And the first term of jp of x is, what is jp? Where we have here plus. The first term of that will gives you minus 1 raised to 0 upon 0 factorial p factorial x by 2 power p. And this is bounded. Bounded for x is equal to 0. Similarly, this jp is bounded for near to x is equal to 0. But this j minus p is not bounded near x is equal to 0. For each term, we can say that. So that means one of them is bounded, another one is unbounded. That means this jp and jp minus 1, they are independent. So in this case, we can able to write down as a general solution. So we can write down similarly for each term of jp of x, it is bounded near x is equal to 0. Hence, j minus p of x and jp of x are independent. So we can say that the general solution is c1 y1 plus c2 y2 will be c1 jp of x plus c2 j minus p of x is the general solution of 1. In the case of p is not an integer, in that case of that, we can have this is a general solution. Now the case number 2, that we can discuss that if p is an integer, let p will be m, or I can say let p will be an integer. Then we can find another solution using the following formula, that we know the formula is y2 equal to vy1, and where this v can be calculated as v dash is equal to 1 upon y1 square integration minus p dx is there. This is the way is to calculate this y1. But here what we are doing, we are not doing in this manner. We are use some strikingly different method for simplicity. If you go in this manner, then it is more difficult and more calculative work will be there. So we'll approach some another method. But here we use different method for simplicity. Let us define yp of x will be cos p pi jpx minus j minus p of x upon sin p pi. Now the question is how we think someone is think of this function. That is the question. Union 0 and p is not an integer. Then what we want is the equation or the solution can be written into the form that y equal to c1 jpx plus c2 ypx as c1 dash and c2 dash. I'm just using c1, c2 is already used above, so that's why this is c1 dash, c2 dash. So that is yp of x. We can just substitute here value. So that is cos p pi into jp of x minus j minus p of x upon sin p pi. So if I combine the terms of jp and jp minus 1, this will be c1 dash plus c2 cos p pi upon sin p pi into jp of x. To combine these two terms, that is this one and this c2 into cos pi and sin pi. So this one upon this one. So that I have written separately. Minus, because this is minus sign, minus c2 upon sin p into pi j minus p of x we have. And this quantity, I may call it some another constant, that is c1 jp of x plus c2 j minus p of x. And since we define this yp is defined as a specific manner, in a specific manner, the limit p tends to m, yp of x is exists, because otherwise this we cannot write. But this ym, if I replace p equal to m here, then we know that j minus m of x is a negative, and in that case it is the unbounded. So this ym is also unbounded, so that we know. So but ym of x is unbounded, so it is infinite. We define ym of x is equal to limit of p tends to m yp of x. Then y1 y is equal to c1 y1 plus c2 y2, which is c1 jm of x plus c2 ym of x, and which is the general solution of equation 1, which we have a Bessel's equation. And this completes the writing the solution of the Bessel's equation we have. Okay.